Hello everyone, today we are going to set up our cadence for 180 nanometer technology and followed by one simulation of simple CMOS inverter and its power and delay calculation. So in order to set up our cadence, we need to start Xming first. So double click on Xming. You can see minimize window of Xming over here, and after that open Putty. Select the setting which we have previously saved for our CCAD server, that is CCAD X11. Click on that and click on open. It will open one pop-up window and it will ask you for your login, and so you need to log in with your e-reader ID and e-reader password. So as you're logged in, it will show you that your e-reader name followed by the CCAD. That means you have successfully logged onto the server. Now in order to set up your 180 nanometer cadence technology file, we will follow our rules which are prepared for 180 nanometer. So for 180 nanometer technology, we are supposed to make one directory by the name cadence underscore 180 nanometer technology. Then we'll be going into that particular directory and we'll copy our related 180 nanometer technology file in that particular folder, and we'll be accessing those files from that folder each and every time. So let's type one command, mkdir cadence underscore 180 nano. I have already created this directory in my particular folder, so I'm not going to write this command right now. Once you press enter, it will create the directory automatically. So in order to check whether the directory is created or not, type ls, which will show all the folders and files which are there in your folder. So press enter. You can see this folder, cadence 180 nanometer. This is the folder which you created just now. So in order to enter into that folder, type cd followed by the name of that folder, which will take you to the folder. You can see that in the path. After that, you are supposed to copy some files from the server to your folder. In order to do that, let's open this path and you can directly type that path. Make sure that there is space after cp followed by the path. Make sure that there is a dot at the end and then press enter. So this means we have successfully copied the necessary files from the server to your folder. Again, in order to access those files, you need to type these three commands, which will ultimately take you to the cadence window. To do that, csh followed by underscore 180 nanometer .sh, and in order to open cadence, type virtuoso. Press enter and this command will take you to the cadence window. There will be two or three windows that will pop up. One is the library window and there is a log window. We can see this is the log window, and this window is most important because in order to access your cadence, you need to keep this window active this window will give you the log of your all the activities, so we can just minimize it for now. This is our library window, and you can see all the libraries to the left side of this. These are all the libraries which are currently present in your 180 nanometer technology folder. In order to draw your own schematic, you need to create your own library. In order to do that, click on File, New, and Library. You're supposed to give some name for your library. Let's say it's demo, and click on OK. There will be one pop-up, and it will ask you whether you want to compile your ASCII technology file, or to refer existing technology file, or to attach existing technology library. So we are going to select the third option, and this command will attach your current library to the one which you select over here. I will be selecting the first library which is associated with the 180 nanometer technology. Then click on apply and OK. Now you can see your library demo over here. In order to draw a schematic in that particular library, you need to click on that particular library. You need to select that library, and then again go to File, New, and Cell View. We'll be drawing a schematic for inverter circuit. So type, let's say it's inverter. You can give any name, but for time being I'm giving the name inverter. Click on OK. There will one pop up. It will ask you about the license, and click yes on that. You will see one schematic window over here. Now we will be referring some shortcut keys which I have already mentioned in the PDF file. These are some shortcut keys like insert instance, press I; to copy, press C; to edit component properties, press Q, and so on. You can refer all these properties, all these shortcuts. So we'll be using a few shortcuts from that right now. So go to your schematic window, press I in order to get a component. There will be one component browser, and you're supposed to browse the necessary component from that. In order to get your NMOS and PMOS, select the first library, that is NCSU analog parts, and from that search for the N transistors and go for NMOS 4. You can see the width is like 300 nanometer and length is 200 nanometer, which is the rounding off of 180 nanometer. So you can minimize it, and you can place your NMOS anywhere in the schematic. Similarly, we will be going for our PMOS. You can browse in your component browser, or else you can make a change over here, like you can type PMOS 4 in the cell name, which is the same. So it will give you one PMOS, and you can place your PMOS over here. Now you're supposed to give power supply and ground. So to do that, press I again. Again open component browser and select the library, analog library, and select sources. There are multiple types of sources like dependent, global, independent ports, and set domain. So we'll be going for global, and to select ground, click on ground. So there will be ground. Again, in order to draw a VDD, you can browse all the way for the VDD, or else the other way that you can do is you can type VDD. Make sure that whatever the name you typed is similar to the name of the component in the current library. So type VDD and then say enter. It will give you a VDD source. Place it over here. Now you all are supposed to give inputs and outputs, as we are dealing with only single CMOS inverter. There will be only one input and one output. In order to do that, press P, which will make you insert pins. Let's say in is your input. Make sure that the direction of input is input, height, and place the pin accordingly. Again press P. Let's make one pin output. Select the direction to be output, hide it, and place it. Now you are done with everything except the connections. Press W, which will enable you to draw wires, join all the floating points according to your circuit. Alright, so you're done with your circuit, and once you are done with your circuit, you can check it and you can save it. You can click on this particular symbol, like with the green check-in sign. This is check and save. It will save this schematic for you, as well as it will find whether there are some errors or not. So click on this particular symbol. So as we have said, it said that there are two warnings. In order to find those warnings in your schematic, you can see that there are some yellow squares over here. That yellow squares indicate that there is some error. So as we can see, the body connections are missing. So again press W in order to connect your body of your PMOS to VDD and body of your NMOS to ground, and again click on check and save. Now so far we have done with our design, but we will be maintaining a 2:1 ratio for the CMOS inverter. So as the width is 300 nano, let's make the width of PMOS 600 nano. In order to access properties of this particular PMOS, select the PMOS and press Q, which will take you to the property of that particular PMOS, and change the width over here. Let's make it 600 nano and press enter. So right, we have 2:1 proportion for this particular CMOS inverter. Again check and save. So we are almost done with our design. In order to carry out the simulation, you need to click on the launch ADEL, that is analog design environment, and it will again ask for the pop-up for the license for this particular thing. Click on yes. Now in order to carry out the simulation, you need to make some initial setup. So to do that, click on setup and select a simulator directory. We will be using the Spectre, so select Spectre from here and then click OK. Again you are supposed to select model library files. So in order to do that, select on model libraries, and it will ask you to browse your model libraries from a folder. So click on that. You will see one folder by name 180 nanometer models. Double click on that and you will see two model files, for one is for NMOS and one is for PMOS. Select both of the files and open it and click on apply and OK. So this command will add you model libraries to your design. Again, in order to give input and output signals and the power supply, click on setup and stimuli. There will be one pop-up and you can see your input over here, that is in, and which is currently in off condition. In order to make it active, click on enable, then select the function of your input. Let's make it pulse, as you are using 180 nanometer technology. Let's say the power supply is 3.3 volt, period of 40 nanoseconds with no delay time and rise time of 10 pico, fall time of 10 pico, and let's say the pulse width is 20 nano. That is, we are maintaining the 50% duty cycle for this particular signal. Then click on apply. As you can see, the current input signal is a voltage pulse with 3.3 and 0, and which is in on condition. In order to access the power supply, you can see, click on the global sources and you can see your VDD, but which is again in off condition. So in order to make it on, click on enable function. Let's make it DC, and DC voltage, let's make it 3.3 volt. Again click on apply and OK. So you are done with stimuli, and now you are supposed to calculate the simulation. So to do that, choose analysis, and we'll be selecting the transient analysis, that is the very first analysis, and let's make it to the 100 nanoseconds. Enable this, apply, and OK. So far as we are done with our setup. In order to save our outputs, in order to plot our outputs, click on outputs to be plotted, or else one thing you can do before plotting your outputs, you can save all the outputs which are related to your design. So click on save all and select the signal to output save all, click all for power signals, and click all for device currents. Again apply and OK. Now you're supposed to select your inputs and outputs which are to be plotted. So to do that, click on output to be plotted and select on design. You can select your input as well as your output on the design. Once you select them, you will be click on this particular symbol, that is green circle with white triangle, which will run your simulation. As you can see, there are two windows. One window is having some text and numerical files in it, which is nothing but a netlist file for this particular simulation, and other file is the waveform which are plotted. You can see your input and output symbols over here. So in order to split those signal, click on graph and split all strips. It will show your input and output. You can also change the width and length of this particular signals. Click on medium. Again the output, let's make it medium. You can also change the color. Click on color and let's say it's blue. So you can see the blue one is your input and red one is your output. You can customize it in the way you want. You can also change the background. Right click, graph properties, and you can also change the background color if you want any. Let's make it white for now, so we can clearly see our output over here. In order to calculate the delay, again we will be combining those signals, because in order to calculate the delay, we'll be dealing with the switching of input and output at the same time. So we will combine all those two signals. Again, these dark lines are nothing but the switching of input and output at the same time. So we will be zooming in for this particular area in order to check the delay. So you can see the scale right above your graph, and the scale is nothing but the smaller version of your waveforms. And in order to zoom at this particular point, you are supposed to drag these rulers towards the particular point. As you can see, there are some minor changes in your output depending on your input. So as you can see, the switching is very clear in between input and output. So in order to measure your delay, we will add some marker. So in order to do that, click on marker and create marker. There are three options. One is point marker, horizontal marker, and vertical marker. Point marker is especially for one single point which we'll be dealing with. Horizontal marker, it has a fixed y-axis, and vertical marker has fixed x-axis. In this case, we'll be using the horizontal marker, as we have 50% of input and 50% of output. So that is nothing but half of 3.3 volt. So, and one important thing, that we'll be calculating the delay, like the time after when the input reaches to the 50% of its value to the time when output reaches to the 50% of value. By calculating the difference between the both, we will be calculate the delay. So let's insert the components, which is half of the VDD, that is 1.65, as your VDD is 3.3 volts. Click OK. You can see two numbers over here, First is the time taken by input to reach its 50% value, and other is the time taken by output to reach its 50%. By calculating the difference in the both values, you can calculate the average time. This is not the actual delay, or this cannot be the actual delay, because we are considering only one transition from input and output. This can be the average delay for this particular design. Now, in order to calculate the power, you need to click on the tools and click on result browser, which will browse all the results for you. There will be one pop-up, and again in that you are supposed to click on the tran, and in the bottom of the part you can see one PWR, that is the power, total power of the circuit, or power parameter. You can right click on it and click on calculator. You will see one calculator with different functions, different things. So in order to do that, you can see here get data and power. So there will be one function panel right below it. Select all and select the average. That will give you the average power consumed by the circuit. And in order to calculate the power, click on this signal, which is the evaluate key. Once you click on it, it will give you the power, that is around 0.9 microwatt, or you can say 908 nanowatt, which is nothing but the average power of the particular circuit. So this is how we have calculated the power and delay, which are in average power and average delay, you can say, of the circuit. In order to save the current setting or current simulation setting, click on the session and again click on save state. If you choose the cell view, that will be preferable, so click on the cell view and click OK. Give some name for the particular cell view, click OK. So your all the settings are automatically saved. Now if you once you save this, you do not need to open the ADE again and again. You can check your library manager, and in front of your schematic there will be one state which is nothing but your ADE state. Once you double click it, it will give you that window. So this is how you can implement a circuit in 180 nanometer technology file and calculate its delay and power. Thank you.